The most successful space engine humanity has ever flown beyond the moon doesn't roar. It doesn't shake the launch pad. At full power, it pushes on your spacecraft with about the force of a single sheet of paper resting on your palm. That's it, a whisper. And yet, that whisper is the reason a NASA probe called Dawn was able to do something a roaring chemical rocket physically cannot: visit 2 different worlds in the asteroid belt, one after the other, on a single tank. Here's the strange truth about getting around in space. The engines that feel powerful are mostly useless for the journey, and the engines that feel pathetic are the ones that actually win. So today, we're going to climb the entire ladder of space propulsion, from the violent chemical rockets we use now, up through the plasma engines quietly flying today, into the nuclear and antimatter machines that might exist someday, all the way to the warp drives and faster-than-light dreams that almost certainly never will. And along the way, the real prize, figuring out which of these are real engineering, which are long shots, and which are beautiful ideas that physics has quietly already killed. Let's start with what's strapped to the bottom of every rocket you've ever seen launch: chemical rockets. Burn fuel, throw the hot exhaust out the back fast, get shoved forward. Every crewed launch in history runs on this, and they have exactly one thing going for them, but it's a big one: raw thrust. A chemical engine can produce millions of pounds of force, enough to rip a skyscraper-sized machine off the planet against full gravity. Nothing else on this list can do that. If you want to leave Earth's surface, chemistry is still the only game in town. But chemical rockets have a brutal, inescapable weakness, and to understand the whole rest of this video, you need to understand it. We measure an engine's fuel efficiency with a number called specific impulse, basically how much push you get per unit of propellant. The higher the number, the less fuel you burn for the same effect. A good chemical rocket scores somewhere around 450 seconds. That sounds abstract, so here's what it means in practice. Chemical rockets are absurdly thirsty. They burn through colossal amounts of propellant in minutes, which is why a rocket is basically a giant flying fuel tank with a tiny payload on top. They're sprinters. They give everything in a few glorious minutes, and then they're empty. For crossing the solar system, that's a disaster. Which is exactly why, once you're already in space, the smart move is to throw away the sprinter and bring in the marathon runner. Enter electric propulsion, the family of engines that includes that paper-thin Dawn thruster. The idea is elegant. Instead of burning fuel chemically, you take a gas, usually xenon, strip its atoms of electrons to turn them into charged particles called ions, and then use electric and magnetic fields to fling those ions out the back at staggering speed, tens of kilometers per second, far faster than any chemical exhaust. The thrust is tiny, yes, that sheet of paper push, but the efficiency is extraordinary. An ion engine's specific impulse isn't 400 seconds, it's several thousand. NASA's next ion thruster ran continuously for the equivalent of more than 5 years in a single ground test. 5 years of firing without stopping. That's the marathon runner. It pushes feather light, but it never gets tired. And over months, that gentle shove builds and builds until the spacecraft is screaming along at speeds no chemical rocket could ever reach on the same fuel. There's a whole zoo of these electric engines, and they matter because they're not theoretical. They're flying right now, on hundreds of satellites. Hall effect thrusters are the workhorses, using a clever magnetic trick to ionize and hurl propellant. They're on commercial satellites and were used by China's spacecraft for maneuvering in high orbit. And then there's the ambitious one, Vasimer, a plasma engine that uses radio waves to superheat its propellant into a plasma hotter than the surface of the sun, contained by magnetic fields because no solid material could ever touch it. Its party trick is shifting gears like a car, trading thrust for efficiency on the fly. The catch, and it's a recurring villain in this whole story, is power. A Vasimer prototype needs around 200 kilowatts of electricity to make a few newtons of thrust. Where, in deep space, do you get that kind of power? Hold that question. It's about to eat the next 3 engines alive. Because if power is the bottleneck, the obvious answer is go nuclear. This is where we cross from flying today into should exist, doesn't yet. There are 2 flavors. The first is nuclear thermal propulsion. A A nuclear reactor heats hydrogen to extreme temperatures and blasts it out a nozzle. It's like a chemical rocket, but the energy comes from splitting atoms instead of burning fuel. And it's roughly 2 to 5 times more fuel efficient than the best chemical engines, while still producing serious thrust. On paper, it could cut a crewed trip to Mars dramatically, which is exactly why both NASA and the Pentagon's research arm announced, with great fanfare in 2023, a joint project called DRACO to fly a nuclear thermal engine by 2027. And here's a fact that tells you everything about how hard this field is. In 2025, they killed it. The 2026 budget zeroed out DRACO entirely, and NASA proposed abandoning its nuclear propulsion programs too. The reason is almost more interesting than the technology. As launch costs collapsed, driven by reusable rockets, the enormous cost of developing a flight-ready space reactor started to look like a worse and worse deal. The engine wasn't impossible, it just stopped being worth it. That's a recurring way these futuristic engines die, not because physics forbids them, but because reality outran them. The second nuclear flavor is nuclear electric propulsion. Use a reactor to generate electricity, then feed that electricity to those efficient ion or plasma engines we just talked about, finally solving their power problem. This is, in many ways, the dream pairing for deep space. Nuclear power plant plus marathon runner thruster. But it means flying a full nuclear reactor and a way to dump its enormous waste heat in vacuum. And it too has struggled for funding and engineering maturity. It remains perpetually a couple of decades away. But there's a third, far wilder nuclear idea, and it's the most insane engine ever seriously studied by a government. It's called Project Orion, and the plan was exactly as unhinged as it sounds. You propel a spaceship by detonating nuclear bombs behind it, one after another. The ship rides on a massive armored pusher plate mounted on giant shock absorbers, and you drop atomic bombs out the back, a few seconds apart, and let each explosion slam into the plate and shove the whole craft forward. This was not a napkin sketch. It was a real, funded program starting in the late 1940s, championed by legendary physicist Freeman Dyson, and the numbers were staggering. An Orion ship could have hauled thousands of tons, entire cities' worth of payload, across the solar system. Performance no other engine on this list comes close to. Each blast against the plate would produce something like 50,000 times the force of Earth's gravity, which the shock absorbers had to smooth into a survivable push. It is, to this day, one of the only starship designs we could plausibly have built with mid-20th century technology. So what killed it? Not physics. A treaty. The international ban on detonating nuclear weapons in space and the atmosphere made launching a bomb-powered rocket politically impossible, and the fallout from flying one out through the atmosphere was unconscionable. Orion is the ultimate example of the theme of this whole video, an engine that worked on paper, killed by everything around the paper. Now let's do something completely different, an engine that carries no fuel at all, the solar sail. Light has no mass, but it does carry momentum, and when it bounces off a mirror, it gives a tiny push. Make that mirror enormous and gossamer thin, and sunlight alone can accelerate it. No propellant, ever. This isn't a fantasy. In 2019, a small craft called LightSail 2, funded entirely by tens of thousands of private donors, unfurled a sail the size of a boxing ring in orbit and measurably raised its path around Earth using nothing but photons. It worked. The push is fantastically gentle, far weaker even than an ion engine, but it's free and endless. And unlike every other engine here, it never runs out. And the solar sail is the gateway to the single most credible plan we have for actually reaching another star. Don't rely on the feeble sun. Build a ground-based laser array and fire it at the sail. This is the premise of Breakthrough Starshot, a 100 gigawatt laser blasting a postage stamp-sized chip with a tiny sail, accelerating it to 20% of the speed of light in minutes. At that speed, it could reach the nearest star system, Alpha Centauri, in around 20 years instead of tens of thousands. The physics genuinely works. The engineering, a laser more powerful than the entire output of many countries, aimed with impossible precision, is the part that keeps it a dream for now. But notice, This is the first engine on our list that could, in principle, take something human-made to another star within a human lifetime. There's also a quieter cousin to the light sail that most people have never heard of, and it doesn't use light at all. The sun blows out more than just photons. It throws off a constant stream of charged particles called the solar wind. Two clever sail concepts try to ride that wind instead. The magnetic sail, proposed by Robert Zubrin in 1991, uses a giant loop of superconducting wire to generate a magnetic bubble that the solar wind pushes against. And the electric sail, invented by Finnish physicist Pekka Janhunen in 2004, is even stranger. Instead of a physical sail, it unreels dozens of bare wires, each tens of kilometers long, and charges them to high voltage, creating an invisible electric field that deflects the solar wind's protons and steals their momentum. No fabric, no fuel. A sail made of pure electric charge, kilometers wide, weighing almost nothing. It's been the subject of serious NASA study as a way to fling probes to the edge of the solar system fast. These are real concepts on the engineering bench right now, just waiting, like everything in the almost real category, for someone to actually fly them. Past this point, we leave the realm of hard but buildable and enter the engines that live mostly on paper. And the first is the next rung above fission: fusion. If splitting atoms gives you a great engine, fusing them, slamming light atoms together the way the sun does, gives you a far better one, with more energy per kilogram of fuel and no need to haul bombs. The most famous serious design is Project Daedalus, a study by the British Interplanetary Society in the 1970s for an uncrewed starship. The concept? Drop tiny pellets of deuterium and helium-3 into a magnetic chamber and zap them with electron beams hundreds of times per second. Each one a controlled micro-explosion of fusion, the plasma channeled out the back by magnetic fields. Daedalus was designed to reach a nearby star within about 50 years. A two-stage behemoth so large it would have to be built in orbit. The physics is sound. The problem is that we still cannot make controlled fusion produce more energy than we put in reliably here on Earth, in giant laboratories, let alone in a compact engine firing pellets in deep space. Fusion propulsion is real in principle and waiting, perpetually, on a fusion breakthrough we keep almost reaching. And there's a gorgeous variant that tried to solve fusion's other problem, carrying fuel. The Bussard ramjet imagines a ship that scoops up the thin hydrogen drifting in interstellar space using an enormous magnetic funnel, compresses it, fuses it, and blasts it out the back. A starship that gathers its fuel from the void as it flies, accelerating forever without a tank. It's one of the most beautiful ideas in all of propulsion. It's also, by recent analysis, almost certainly dead. The interstellar medium is so absurdly thin, roughly 1 atom per cubic centimeter, that the magnetic scoop you'd need would have to stretch something like 150 million kilometers across, the distance from the Earth to the Sun, and the drag it created would likely cancel the thrust. A perfect idea, undone by the emptiness it was meant to harvest. Now, the ultimate fuel: antimatter. When matter meets antimatter, both are annihilated and converted almost entirely into energy, the most concentrated energy release physics allows, vastly beyond nuclear fission or fusion. A few grams of antimatter, in theory, holds the energy of an enormous chemical fuel tank. An antimatter rocket would be the most powerful engine conceivable short of breaking physics. So why don't we have one? Because antimatter is the most expensive substance in the universe. We can only make it a few atoms at a time in particle accelerators at a cost that runs to trillions of dollars per gram, and we can barely store it. It annihilates the instant it touches ordinary matter. To fuel a starship, you'd need to manufacture and bottle quantities we currently produce in amounts invisible to the naked eye over years. The energy is real. The engineering gap is so vast it borders on the absurd. And now, the one everyone's been waiting for. The warp drive. Faster than light. And here's where I have to be honest with you, because this is where the dream meets the wall. In 1994, a physicist named Miguel Alcubierre did something clever. He found a real solution to Einstein's equations that describes a warp bubble, a region where space itself contracts in front of a ship and expands behind it, carrying the ship along faster than light without the ship ever locally breaking the light speed limit. It's mathematically valid. It is, in the equations, a genuine way to travel faster than light. For decades, this kept the dream alive, and NASA even ran a small lab investigating it. But the Alcubierre drive comes with a price tag written in the laws of physics, and it's a killer. To bend space that way, you need something called negative energy or negative mass, a substance that pushes instead of pulls, that falls up instead of down. And here is the quiet tragedy. As far as we can tell, that substance does not exist. Our best recent experiments confirmed that even antimatter, the most exotic stuff we can make, falls down in gravity like everything else. The one loophole people hoped might provide a source of anti-gravitating material slammed shut. Without negative mass, the warp bubble needs a configuration of matter the universe doesn't appear to allow. And early estimates of the energy required were beyond astronomical, more than entire stars could provide. Newer theoretical papers keep trying to reduce that cost, even sketching warp geometries that don't need negative energy at all. But they come with their own catch. They can't exceed the speed of light. The faster-than-light version, the Star Trek version, still requires the one ingredient nature seems to have refused to stock. Which brings us to the engines that aren't long shots, but mirages, the ones that violate physics outright. For years, headlines buzzed about the M drive, a closed metal cone you pump microwaves into that supposedly produced thrust with no propellant at all. A reactionless drive. If real, it would have rewritten Newton's laws. Every action having an equal and opposite reaction is as fundamental as physics gets. Tantalizing early tests, even at NASA, seemed to measure a faint push. But when researchers in Germany built one and tested it with truly sensitive equipment, shielding against every stray effect, the thrust vanished. It had been an artifact all along, the device essentially pushing against Earth's own magnetic field, against the test cables, against measurement error. A null result. The impossible engine was impossible after all. So where does that leave us, standing at the bottom of the ladder looking up? The honest map looks like this. Chemical rockets get us off the ground and always will. Ion and plasma engines are quietly conquering the solar system right now, one patient Newton at a time. Solar and laser sails are real, flying, and may one day fling a sliver of humanity toward another star. Nuclear engines work in principle, but keep dying on the spreadsheet. Antimatter is real energy locked behind an impossible price. And the warp drive, the dream that the stars might be a weekend away, sits behind a door that physics, so far, has bolted shut from the other side with a substance that doesn't exist. The dirty secret of space propulsion is that the universe isn't waiting for us to be clever enough. For most of these engines, we already know how they'd work. What we don't have is the power, the money, or in the case of the warp drive, the permission of physics itself. Here's the number that puts it all in perspective. Voyager 1, the fastest, farthest human object ever launched, has been flying for nearly 50 years and is now over 20 billion kilometers away. It is moving at about 17 kilometers every second, and at that speed, the best we've ever actually achieved, reaching the nearest star would take it roughly 70,000 years. Not a typo, 70,000 years to the closest star, with our real, flown technology. Every engine in this video is, at bottom, an attempt to turn that 70,000 into something a human could live to see. We didn't fail to invent the warp drive. The universe just never built the road.